All right, I think we can slowly get started. Welcome, everyone. My name is Matas Luca. I'm co-founder of Blue Guardrails. This is our first live session, in fact, where we want to share with you the work we did on PlaceboBench, a benchmark of state-of-the-art large language models in the pharmaceutical domain. So with that being said, I think I can hand it over to Miriam here, who will present the first part of this session.
All right, yeah, welcome everybody. My name is Miriam. I'm also co-founder of Blue Guardrails. And I would say let's just dive right in. We don't have a lot of time. So yeah, this is about creating hallucination-resistant GenAI applications in pharma, but it also kind of applies to a lot of other topics. You will see that. A few weeks ago, we published PlaceboBench, a benchmark to see which one of the LLMs that are out there currently and that are state of the art are actually best performing on a pharmaceutical use case. And I will start out by telling you how we tested that. So the use case that we tried out is, let's call it a medical assistant. It's a pretty standard RAG use case. So we start out with a query. For example, does Ozempic, semaglutide have to be tapered before discontinuation, or can it be discontinued abruptly? I'll tell you more about these questions in a second. Then we have a retrieval step that goes and has access to more than 2,500 summary of product characteristics. That's basically patient leaflets for medications, but more sophisticated for doctors and pharmacists. They are published by the EMA, the European Medicines Agency. We stored those in a vector DB. So the retriever went and found the most relevant documents to the question that was posed. Then we feed the question together with those relevant documents into the prompt, and the prompt is then sent to the LLM that generates the answer. So for example, Ozempic does not need to be tapered before discontinuation, however, and so on. So you know the deal. That was the use case that we set up to be able to test the performance of these LLMs. How did we go about benchmarking itself? So we had 69 of these queries that I just showed you from human doctors. They were Swedish and Norwegian doctors and pharmacists, and they had asked these questions to their local health authorities, and you could find those questions online. So that was kind of our basic data set that we used, and we fed those into the RAG pipeline you just saw. Of course, we had to translate them from Swedish and Norwegian to English. And then we went and annotated those answers that we got on a claim level, meaning you can see it on the right here. We really went through every single claim in an answer and checked, is this actually grounded in the documents that were provided to the LLM, or is it not, basically? So you can see customer at the pharmacy asks if Ajovy can be used on tattooed skin. The tattoo is not new. And then part of the answer was Ajovy should not be injected into tattooed skin, regardless of whether the tattoo is new or old. And this second part of this sentence is a hallucination. That's how we annotated it. We had 8 different categories of hallucinations. I'll tell you a bit more about that in a second. And we tested it on 12 LLMs. The first round, you can see the first LLMs that we tested in green here. And the second round we did is the ones in blue. So as I said, 12 of them for all of the large vendors, so Google, Anthropic, OpenAI. We took their flagship LLMs, basically the big ones, you know, the famous ones, as well as their cheaper and smaller alternatives. And as an open weights alternative, we chose Kimi K25. And yeah, as we did this already 4 weeks ago, of course, in the last 4 weeks, we had 5 major releases from the big vendors. So of course, we freshly added those to our leaderboard actually today. So you will find very fresh learnings in this session. So about the findings, what we saw in our benchmark is a lot of the hallucinations were fabrications. That's basically, the classic hallucination. It's information that's basically made up. It has no grounding in the source documents. It's made up. But what we also saw a lot is, for example, the insertion of world knowledge. Even though we prompted the LLMs to not use their own trained world knowledge, to only rely on the documents provided, they still did that a lot. So those are just 2 of the 8 categories that we used. And I'll show you some examples for some of the other ones. So what happened quite a bit was that the frequencies of side effects were reported wrong. So in this case, you can see that Gemini 3 Flash identified a side effect as common instead of uncommon. So in the pharmaceutical realm, that's a huge difference, actually. So you can't just go and report that with a different term. It's just a whole different information. So we annotated that as a contradiction because the correct information was there, but it was reported wrong. Another example would be a terminology case. In this case, it was Kimi K25. It describes a live vaccine as contraindicated, but in the source documents, it was called not recommended. Again, the terminology in the pharmaceutical realm is, has to be very precise, and you can't just use a word that kind of sounds right to describe something that's actually something else. So the 2 things, being not recommended and being contraindicated are 2 different things. So this is how we went along and annotated the whole data set. About the hallucination rates, of course, that's what we were looking for mostly, right? The hallucination rate is the percentage of model responses that contained at least 1 hallucinated claim or more than 1. So our initial leaderboard was this. We saw significant differences in the performance of the models. You can see here, Gemini had a hallucination rate, Gemini 3 Pro had a hallucination rate of, let's say, only 26.1%, and performed so much better than, for example, the big Anthropic Opus 4.6, right? Even though that was very recently released, pretty famous for a lot of things. But we saw in this use case that we posed, it did not perform very well. So we saw hallucination rates between 26 and 64 almost. And then, as I said, we added 5 more models that were released in the last 4 weeks. So that kind of completes the picture for today. Let's say, who knows when the next release is coming. We saw, again, Anthropic Sonnet 4.6, very similar to, let's call it the big brother, Opus 4.6. And then Gemini 3.1, pretty similar to Gemini 3 Pro. But what's interesting here is that GPT 5.4 and Gemini 3.1 Flashlight took over the leaderboard. That was a big surprise for us, especially, and we'll dig into that a bit more later, especially as the Flashlight model is pretty cheap, actually, and it's performing really well here. So this is the overview of all the models we looked at. Especially surprising to us really was how badly the new Sonnet and the new Opus models performed. We were almost disappointed in that, actually. So they rank very high in general leaderboards and especially in coding leaderboards. They're very famous. But what we noticed, and that's very peculiar about the use case we tested, they had a very strong tendency to apply their own world knowledge, which we did not want. And they had a very strong tendency to appease. So they wanted to give advice and be helpful and, give recommendations. But really, the last thing you want from an LLM when it comes to medications and drugs is that it gives you advice that you don't really know where it's based off of. So for us, that was very unwanted and therefore part of why they performed not so well. Now, while GPT 5.4 and a few of the Gemini models seem to behave pretty similarly, we have to also look at the cost and the latency, because when you pick an LLM, that's also definitely a consideration. And this, it looks chaotic, but it's actually pretty easy. So you see on the y-axis the hallucination rate, and on the x-axis you see the latency on the left and the cost on the right. And 3 of those of the Gemini models, you can tell they're pretty low on the hallucination rate, as we just saw, and they're also in an acceptable range of latency and cost. And the other models that have a, let's say, acceptable hallucination rate, like GPT 5.4, are just very expensive and very slow. And we'll dig into that a bit more in a few minutes. So definitely you can see the Gemini models are the star of the show, the star of the pharma use case show for sure. Very surprising to us, cool finding. And I think if you take away one thing from PlaceboBench, it should be that neither size nor cost nor, let's say, fame of a model really indicates if it's going to do well on your personal use case. So whatever you build, you have to make sure you're using the right model for this specific thing that you need from them. And now, even with a okayish hallucination rate of 26 or 24%, you still want to manage that. You still want to get better on that, right? So we've tried a few things, and Matas are going to look into that with you.
Yes, thanks, Miriam. I'm going to talk about, okay, now that we know that all of these models hallucinate, what can we do about it? And we tried out a few different things, either based on our experience or based on experiments that we did with the benchmark. And we identified 4 areas that have a strong impact on the hallucination rate. The first one is thinking effort. How many thinking tokens does the model produce before answering? Data and metadata, system prompt, and structured outputs. I'm going to jump into the thinking effort first. Here you can see the difference between the number of thinking tokens, kind of invisible tokens that the model uses to think, are produced, and how many output tokens. And you can see that on average, all models produce answers of a similar length, a similar token count, somewhere around 70 to 120 tokens on average. But the number of thinking tokens is actually wildly different. So GPT 5.4 mini tops our thinking token leaderboard here with almost 7,000 actually thinking tokens produced per answer. What does that mean? It means it's a lot more expensive and a lot slower. If you take GPT 5.4, for example, that's a model cost-wise, it's on par with Gemini 3.1 Pro, but the difference was really big actually in actual costs because it produced so many more thinking tokens that, of course, also get billed. And also the difference in latency, as Miriam said, 60 seconds for GPT 5.4 versus something like 20 seconds for Gemini 3 Pro. So that has a big impact, thinking tokens. For your use case, you need to think about how much thinking budget can I afford, both in latency and cost, and then play with that to see how it changes behavior. For our next point, I'm going to switch over to our product, actually, that we use to run large parts of the benchmark to kind of illustrate what else we looked at and what else is helpful. So the next point on the list is data and metadata. From our experience, we know that if you provide models with information, they need to know where that information is coming from. So in the original setup of our pipeline, we already included that metadata. So in this case here, you can see, for example, that we have a system prompt that I'm going to go into in a bit. And then we have the retrieved documents from the search. And you can see in this part here that we include for every chunk that we retrieve, which product this chunk is referring to, so that the model can make that connection. That was already the case, so the model rarely misattributed content. One data improvement that we could have made but didn't make is in table extraction. So we often saw the model hallucinate when it extracted side effect frequencies from tables, although the information was there, but it just misread what was extracted. So with a better table extraction, it might have been easier for the model to identify which. Just noticing that I'm not sharing actually. Yeah, thanks. So I hope, so yeah. So here I went through system prompt and here the retrieved documents and the metadata that I talked about. And then table extraction would have been something that we could have done. Now, regarding the system prompt, we used a pretty detailed prompt where we talked about the answer style, and we also talked about the faithfulness and precision of the answer. So we told the models, hey, strict faithfulness means never explain technical terms or concepts when they're not explained in the documents, never add any information, and so on. That was really important. After reviewing all of the errors that the models made, we made some changes to the system prompt. So in this example, we added a section here on mistakes to avoid to see if that improves the model responses. And as you can see here, we basically told the model about all the behavior that we observed that we didn't want. We did a few variations of that, and we can report, you can maybe see that here, and then here with the original, that hallucination rate for one of the prompt changes, it actually got worse, which is not what we want. And the other change was on par. So in this case, we could prove that the system prompt can have a strong impact, a negative in this case, but we didn't manage to improve upon our already strong system prompt in this case. And then the last measure that we took is a bit of a creative interpretation of structured outputs. So for some of the models, what we did was we told it to basically, and I'm going to jump into the system prompt changes again. We told it to use structured outputs. And what we said is, you provide the answer in two parts: facts, which only contain the facts, and then inferences, which can contain advice that follows from the identified facts. And our theory here was that, especially Opus and Sonnet were so insisting on giving advice beyond what was said in the documents that we said, okay, models are going to be models. We can maybe just lead that energy elsewhere. And that's what we did. So we can see here, this is the output in facts and figures, facts and inferences, which means for you, you could throw away the inferences maybe if you only want the facts. And you can see here for GPT, for example, how the hallucination rate in facts is actually just 20% or 21%. And the same was visible, for example, in Sonnet. So you remember Sonnet had 60% hallucination rate. If we used the structured output, we got it down to 33%. Not great still, but a lot better. So that's basically the things that we tried. And the main thing that we learned is definitely you need to experiment. You need to experiment to compare all the different properties, the different costs, the different hallucination rates, to see what works for your use case. Now, I'm going to switch back to our presentation and activate the screen again. Okay. So yeah, that's what we tried. Thinking effort, data and metadata, system prompts, structured outputs. Some improve them, some don't, but they're definitely worth experimenting with. I think that's already everything that we have to present today. If you would like to try out our product, we're currently in a closed beta phase where we invite a select group of people. If you scan this QR code and sign up there, you will receive a code, and then you can try out different use cases and measure hallucination rates with your own data. All right. Thanks for listening. Now we have time for your questions. So if you switch to the Q&A tool and put questions in there, we can answer them. Anything you would like to know.
All right, so we already got a question here, which I think is quite fun, and I understand where it's coming from. So the question is, so which one is the best model? What would you say?
Well, I would say I mean, my personal favorite for this use case is, of course, Flashlight, because it's like, I think it would cost like $8 to run 1,000 of these queries compared to the $100 that would cost to run the same queries through GPT 5.4. So for this use case, it's pretty good. Generally, I would say it depends on the use case. You really have to test. It's very hard to make a prediction based on general benchmarks, much harder than I actually thought it would be.
Yeah, and just to add to that, I think we know the space pretty well. You know, we're kind of on top of all the releases all the time, and we had a few surprises when we created this benchmark. So I'm not going to take it for granted anymore that I know which ones are the best models. So yeah, you really have to try it out. All right, maybe next question. Yeah, we've seen this. Yeah. Have you measured how much bias was introduced by RAG? Have you tested them on much more messier lab data just for fun, with contradictions, incorrect information, adversarial environment?
Okay. So we set up the RAG in a realistic way. Basically, as AI engineers, we've built RAG systems since generative AI models have existed. So we have a lot of experience in what production-grade RAG means, and we wanted to provide an environment to the model that is actually realistic. We didn't want to set it up for failure, so we didn't test with contradictions on purpose and so on, because we knew that the models make enough mistakes as it is without introducing additional hurdles. All right, then next question, what impact the temperature settings have on the results? What have you tested? We didn't test different temperature results because most of the models are actually removing them as a setting. So GPT-5, for example, you cannot even set any temperature. Not sure about the Google models right now, but it's kind of going away as a factor. It might lead to different results, though. Okay. Then there's one question about how sensitive are the models to prompt changes. GPT prompts look different from Gemini and those for GPT. Shouting helps for Gemini. Others don't care. Miriam, do you want to answer that?
Yeah, I think on purpose, we chose the same prompt formatting and generally the same prompt for all of the models. Yes, there was this time where, every model provider kind of had their own kind of secret sauce on how to prompt them, and you would really have to pay a lot of attention in these fake HTML tags and all these stuff, all these things. We decided to not do that for the reason that we've noticed a certain fatigue in users in doing that. So it's kind of tiring to, kind of follow up on the newest rules on how to prompt, and generally speaking, it was never so clear if that actually helps. So yeah, we have a feeling that I've heard this actually before, that shouting helps for some models, but did we really have a proof for that? It's a lot of vibe prompting basically. So we decided to just go straight for the same prompt for every single model, no special formatting, nothing crazy, no secret sauce, and just see how that works.
All right, another question from Dan. We're a publisher of Consumer Insights. Hi, Dan. I know the use case. And you appreciate a little bit of variance or word knowledge, but insist on data accuracy. Does that vary your recommendations? I would say to an extent, definitely. Our use case was very strict. Yours isn't as strict for some of the aspects that we would classify as hallucinations right now. In our product, you could actually adjust what should be considered a hallucination. And I would go into that testing with these kind of adjustments, define what's acceptable for your domain, and then have the live detection kind of run over your traffic and see if data accuracy is a problem or not. And that would tell you which model to choose. So again, I think it would need testing to see which model performs best.
Yeah, definitely. Maybe to add on this, not just the model choice is very specific for each use case. It's also really what's bad for you. What is a hallucination for you? In the medical field, as we saw, for example, these omissions, just not mentioning a few side effects, that's really bad. But if you just want to summarize something like an article, or if you have a very different use case, then that might not actually be a problem. So it shouldn't be labeled as a hallucination. So really, you have to be, again, super specific on the use case.
And then one last question in the last minute, maybe. Any chance to get to near 99% correctness? I don't think so. I think you need to take measures outside of just the model. Maybe more like how's the data used? What data is provided to users so that they can check the information easily for better UX, to get to something that is not 99% correct, but still very usable. You can see that in coding agents, for example, where, of course, the models make a lot of mistakes, but there's this whole infrastructure around handling these mistakes, which makes it still a huge time saver and yeah, very useful. And I think the same goes for any RAG pipeline.
Yeah, I think the goal should be usefulness for a RAG pipeline, not perfection. So, there is a certain tolerance by users to deal with some mistakes or something that's not super accurate, as long as in total it still helps you and it's a helpful product and it's useful and I want to use it because it saves me time. I will accept that it's not perfect.
All right. We're at the 30-minute mark here. Thanks everyone for tuning in. We'll send you the recording and the presentation, and we hope to see you around maybe in one of our future events, or if you'd like to try out the product.
All right. Thank you very much.
Bye.
Bye.